What happens when a multi-million dollar compressor train at your refinery suddenly grinds to a halt because of a single turbine failure? Is it a catastrophic blowout or just a routine swap? The answer depends entirely on three numbers, 611 or 612. I am Chandan Chattopadhyay, Process Advisor, and today we are exploring the critical differences between API 611 and API 612 and the invisible forces governing steam turbines in refinery and petrochemical services. Why does one cost five times more than the other? Why does one need a solid forged rotor while the other gets away with the discs shrunk onto a shaft? All the answers are coming up now, and here, let us dive in. Our session is organized into four main pillars. We will start with the fundamentals, defining the application envelopes for each standard. Then we will move into the process design, covering steam chemistry and materials. Third, we will examine critical rotating components like rotors and bearings. Finally, we will conclude with systems and testings, where we discuss the control protection and rigorous soft testing procedure. Let us begin by defining what separates a general purpose machine from a special purpose one. API 611 covers turbines for general purpose applications. These are typically non-critical, horizontal or vertical units, often driving pumps or small fans. A key characteristic is that they are usually unspared, meaning if that the turbine goes down, the process might continue via a backup pump. But the turbine itself has limited steam condition requirements and uses standard NEMA governors. In contrast, API 612 is for special purpose application. These machines are critical and unspared, driving major equipment like centrifugal compressors or large generators. Because there is no backup for these units, they require continuous long-term service and utilize highly engineered components to prevent any unplanned downtime. Let us talk about the physical differences. Physically, the differences are stark. API 612 units feature heavier, often cast steel or fabricated casings, whereas API 611 may use cast iron. In 612 units, the nozzles are replaceable to allow for performance tuning, while they are often integral in 611 designs. Most importantly, API 612 mandates tilt pad bearings for stability, while API 611 might use simpler sleeve or anti-friction bearings. Now, let us look at the operational environments these turbines must withstand. The operating envelopes vary significantly. While a typical API 611 turbine handles steam pressure up to 40 bar and the temperatures up to 400 degrees centigrade, an API 612 can handle 120 plus bar and 540 degrees centigrade. Power output is another major differentiator. API 611 is usually below 1.5 megawatt, while API 612 can scale up to 100 plus megawatt. Steam quality is non-negotiable for special purpose units. API 612 requires superheated steam to prevent erosion in critical high-speed stages. We also see strict material selections such as 12% chromium for bleeding to resist chloride stress corrosion. Additionally, casing insulation is mandated for personal safety and to minimize thermal distortion. Let us look at the rotor, which is the heart of the turbine. Let us look at how it's constructed. For high speed, high temperature service, API 612 mandates solid forged one piece rotors to eliminate the risk of disc loosening. API 611, however, allows for built up rotors where discs are shrunk onto the shaft, which is acceptable for lower speed applications. Design philosophy also differs. Impulse designs, where the pressure drop occurs only in the nozzles, are common in API 611 for their simplicity and tolerance to clearance variations. Reaction designs offer higher efficiency but require much tighter tip clearances and more precise balancing, which is often found in larger API 612 units. Stability is paramount. Bearings play here an important role. API 612 requires tilt pad hydrodynamic bearings to eliminate oil whirl and whip instability at high speeds. These are essential for stable operation across the entire variable speed range of a compressor drive. To minimize steam leakage, labyrinth seals are favored for API 612 due to their high reliability and non-contacting nature. API 611 commonly uses, however, carbon rings, which are lower cost but require periodic replacement. Finally, we look at how these machines are governed and protected. Now, let us look at the digital governor and the other types of governors which are present. API 612 requires digital governors for precise control and seamless integration with the plant DCS. For API 611, you will often see references to NEMA governor classes to define performance. Safety is critical here. Special purpose turbines must use 2 out of 3 voting logic for electronic overspeed protection. This ensures zero common mode failures and can uh, trip and throttle valve in milliseconds. Now let us talk about the brain of the operation. Gone are the days of just turning a manual valve and hoping for the best. Modern API 612 turbines are packed with integrated control systems that handle the heavy lifting for you. Look at these 4 powerhouses of automation. Automatic startup sequencing. This is not just a start button, it's a precise multi step choreography that ensures the turbine warms up and accelerates safely every single time. Speed control and isochronous governing. We are talking surgical precision here. Whether the load drops or spikes, the governor keeps the speed locked in perfectly. Extraction slash admission pressure control. For complex process, The system manages steam entering or leaving at different stages without breaking a sweat. Diagnostic and alarm logging. If something goes wrong, the turbine tells you exactly what happened when, and no more guessing games in the control room. Check out the diagram on the right and see that electronic governor. It's sending a 4 to 20 milliamp signal to the IH converter, which then uses the high pressure control oil to move the massive steam valve in milliseconds. It's a seamless blend of digital brains and hydraulic brawn. If you want a turbine that thinks as fast as it spins, this is the UI you need. All answers for high speed control are right here on this screen. We will discuss dynamics and vibration now, which will deal various aspects of lateral critical speed and other areas. Now, buckle up for vibration physics. Every rotor has natural frequency, speeds where it wants to shake like a tuning fork. If you hit the resonance at a critical speed, the game is over. That's why API 612 mandates a 15 to 20% separation margin from any critical speed. We don't just hope for stability, we engineer it into the map. If your operating range is near a peak, we move the peak. Stability is not an accident, it's a design requirement. But wait, there is more. Stability is not just about the turbine, it's about the entire train. This is where we go deep with vibration and torsional analysis. Lateral analysis mandated for API 612 to predict damped natural frequencies. We are essentially predicting the future to ensure the shaft stays stable under all conditions. Torsional analysis. This is huge. We analyze the entire train, turbine, coupling, and the driven equipment to make sure that they don't excite torsional modes that could snap the shaft like a twig. Residual unbalance. We strictly limit this to ensure smooth operation, often verified by high pressure, high precision soft balancing. Alright everyone, it's time to get into the soul of the machine. Have you ever wondered why we obsess over every millimeter of a rotor? It's because every single rotor has a personality and its natural frequency. Think of it like a tuning fork. If you hit a tuning fork, it vibrates at one specific tone. Well, your turbine rotor does the same thing. It has a frequency where it wants to vibrate naturally, and that frequency is dictated by two things: stiffness and mass. Now, here is where things get dangerous: resonance. This is the danger zone we talk about in engineering. Critical speed occurs the exact moment your turbine's rotational speed RPM matches the rotor's natural frequency. Moving on to the hardware layer, we are looking at the critical monitoring points for a typical turbomachinery train. Everything you see here follows API 670, which dictates the minimum requirements for a machinery protection system. Starting at the top of our list, we have the radial proximity probes, typically installed in an XY configuration at 90 degrees to one another. This measures the actual movement of the shaft within the fluid film bearings, and just below we have axial position probe. Next is the phase reference, often referred to by the trade name key phaser. This provides a once per revolution pulse, which is essential for determining the phase angle of vibration and the exact RPM. For high frequency faults, or machines with rolling element bearings, we utilize casing accelerometer. Finally, at the bottom, we have our slow speed variables, bearing RTDs and thermocouples. While vibration tells us how a machine is moving, temperature tells us about the health of the lubrication and load on the bearing. A sudden spike here is often first sign of an impending bearing wipe. We will proceed now to the testing and inspection section to ensure reliability through test and procedures. Reliability is proven in the shop. While API 611 is okay with 1 hour run, API 612 mandates a continuous 4 hour mechanical run at maximum continuous speed. We verify every vibration level and oil temperature. We even do an overspeed trip verification and a full bearing inspection afterward to make sure that there are zero hidden issues. It's a 4 hour gauntlet to prove the machine is ready for a decade of service. Look at this gauntlet. Both standards require a hydrostatic test, but API 612 takes it to another level. We are talking that a 4 hour mechanical run, an often mandatory performance test, and the ultimate fit check, the spare rotor feet. We test our backup rotor inside the machine before it ships to ensure it works when you need it most. API 611, they don't even a spare rotor feet requirement. How do we see the invisible? NDE, non-destructive exam. The- we use magnetic particle MPI on all forging surfaces, ultrasonic UT to scan the internal soundness of the massive rotor forging and die penetration for weldments and non-magnetic parts. If there is a microscopic flaw hidden in the metal, this test will find and kill the project before it kills your production. We don't take chances with invisible cracks. Let's talk money. Why does API 612 carry a significant premium cost? Because you are buying extreme reliability. You get the solid forged rotors, the tilt pad bearings, the 4 hour test, and mountain high extensive documentation. API 611 is lower cost, lower complexity, which is fine for simple jobs. But for the heart of your plant, the 612 Premium is the cheapest insurance policy you will ever buy. Before we wrap up, remember the two silent killers, lube oil quality and steam purity. Consistent oil filtration API 614 is the number one factor in bearing longevity for these critical turbines. And if your steam is carrying silica or sodium, you're going to face blade fouling and stress corrosion cracking. You can buy the best turbine in the world, but if you feed it junk, it won't last. Take care of your fluids, and your turbines will take care of you. So, what is the verdict? Use API 611 for your simple spared pumps and API 612 for critical unspared heartbeat of your plant. Selecting the right standard is not just an engineering choice, it's a business decision that protects your production for years to come. Knowledge is power. Now you have the tools to choose the right machine for your process need. If you like this video, please share it to your friends and colleagues.